This is Srikanth S, Assistant Professor of EEE Department. In this session, I am going to cover common base configuration of transistors. The common base configuration, the name itself says we are taking base as the common. So this is also called as grounded base configuration. That is nothing but for both the collector and emitter, we are going to make the base as the common terminal. And in this configuration, emitter is the input terminal, collector is the output terminal, and the base is the common terminal. That means the emitter terminal and common base terminal are known as emitter terminal and common base terminal are known as input terminals, whereas collector terminal and common base terminal are known as the output terminals. Here the input terminals will be emitter to base junction. Input will be given to emitter to base junction, and output is taken from collector to base junction. The common base configuration, the base terminal is grounded, so the common base configuration is also known as grounded base configuration. Sometimes common base configuration is referred to as common base amplifier, CB amplifier or CB configuration. And this is the way how we are going to connect the emitter base junction and collector base junction by taking the base as the common point. Here it is of NPN transistor. So when it is an NPN transistor, we have to give emitter will be connected to the N type. Emitter N type is connected to the negative of VBE. Then only emitter base junction will be forward bias, because we need to have, once the transistor is under active mode, we need to have emitter junction should be forward bias and collector junction should be a reverse bias. So in order to achieve that, we have to give the VBE negative is connected to the emitter terminal and VCB positive is connected to the collector of the transistor, so that this collector base junction will be a reverse biased. So the primary side will be forward biased and the secondary side will be a reverse biased. So here, once it is forward biased, the conduction will take place from one layer to another layer. Here this is the current direction IE, and this is the base direction IB, and this is the collector direction IC. The input signal is applied between the emitter and base terminals, while the corresponding output signal is taken across the collector and base terminal. Thus, the base terminal in the transistor is the common for both input and output terminals. Hence, it is called common base configuration. The supply voltage between the base and emitter is denoted by VBE, while the supply voltage between collector and base is denoted by VCB. In every configuration, the base to emitter junction is always forward bias, In every configuration, emitter junction should be forward bias and collector junction should be reverse bias. Therefore, in order to get the emitter junction forward bias, a negative voltage is applied, negative VBE voltage is applied to the base to emitter junction, and the collector to base junction is reverse biased. The common base configuration for both NPN and PNP transistors is shown in the below figure. Here is the common base configuration, how we are going to connect the VBE negative is connected to the emitter and VBE positive is connected to the base, and here VCB positive is connected to the collector and VCB negative is connected to the base. And these are the current directions, how the current will flow in the NPN transistor and PNP transistor. If it is a PNP transistor, then this VBE value positive is connected to the emitter because poles have to repel each other. So if it is a PNP transistor, here it is a PNP transistor. Once it is a PNP transistor, we have to use a positive voltage across the emitter junction. For both PNP and NPN transistors, the input is applied to the emitter and output is taken from the collector. The common terminal is the base. For the sake of understanding, let us consider NPN transistor in the common base configuration. So in order to get the clear idea, we are taking only the NPN transistor in this common base configuration. The NPN transistor is formed when a single p-type semiconductor layer is sandwiched between two n-type semiconductor layers. The NPN transistor is formed when a single p-type layer is placed between the two n-type semiconductor layers. Here the current flow, the base to emitter junction is forward bias by the supply voltage VBE, while the collector junction JC is reverse biased by the supply voltage VCB. Due to the forward bias voltage VBE, the free electrons in the emitter region experience a repulsive force from the negative terminal of the battery similarly holds. That is, whatever the electrons, free electrons from the n-type, because of it is of highly doped, so the electrons from the collector will move from that particular layer to base junction because of negative terminal is connected to the battery. So negative terminal is nothing but negative and electrons both are of negative type, so they repel each other. That's why the electrons in the collector layer are moving towards the junction J1. That is, as a result, free electrons start flowing from emitter to base. Similarly, holes start flows from base to emitter. So because of this, free electrons will start moving from emitter to base. In a similar way, holes start moving from base to emitter. Thus, free electrons which are flowing from emitter to base and holes which are flowing from base to emitter conducts electric current. Here, when the free electrons which are flowing from emitter to base and holes which are flowing from base to emitter, which will conduct electric current. The actual current is carried by free electrons which are flowing from emitter to the base. However, we follow the conventional current direction, which is from the base to emitter. Thus, electric current is produced at the base and the emitter region. In the bipolar junction transistors, whereas emitter is heavily doped, base is lightly doped, and collector is moderately doped. When we have given the emitter base junction as forward bias and base to collector junction as reverse bias, here these electrons will repel the negative battery supply, and when these electrons will repel, these electrons will start moving from N layer to P layer, so that this depletion region size will reduce. Depletion layer size will reduce, and these electrons are going to form the electron hole pairs in the base layer. Once the electron hole pairs are created, those electrons will be moved towards the collector. So once those electrons will move towards the collector, and here collector is connected to positive of supply, so the electrons will be attracted by the positive of voltage. So current flow from the input side VEE to output side VCC. Like this, the current conduction takes place in the transistors. The free electrons which are flowing from emitter to base junction, the free electrons which are moving from emitter to base junction are going to form electron hole pairs in the base layer, and once these electron hole pairs are formed, because of emitter is of highly doped, so more number of electrons will be present. When there are more number of electrons, those number of electrons have to move from one place to another place where we are having from higher potential to lower potential. So here these are, once these are moving from higher potential to lower potential, so the conduction will takes place. From the above figure, it is seen that the width of the base region is very thin. Here from the figure we can see the layer, the electrons emitter layer is more and P layer is very less, and here collector layer is moderately low. So with this, a small percentage of electrons from emitter junction will recombine with the holes in the base region, and the remaining large number of electrons will cross the base region and enters into collector region. A large number of free electrons which entered into the collector region will experience an attractive force from the positive terminal of battery. Here the large number of free electrons which entered into the collector region will experience a attractive force from the positive terminal of the battery. Therefore, the free electrons in the collector region will flow towards the positive terminal of the battery. Thus, electric current is produced in the collector region. Here, emitter current is always greater than the collector and base current. So, always emitter current, because emitter is going to have more number of electrons, so the current flow is also more. So, emitter current is equals to base current plus collector current. Emitter current is equals to base current plus collector current. Here we know that emitter current is the input current and the collector current is the output current. The output collector current is less than the input emitter current. So the current gain of the amplifier is always less than 1. In other words, the common base amplifier attenuates the electric current rather than amplifying it. Here, in the other way, the common base amplifier is also attenuates the electric power rather than the amplifying it. The base to emitter junction is at the input side and acts as a forward bias diode. So the common emitter amplifier has a low input impedance. Common base amplifier has a low input impedance. And on the other hand, the collector to base junction at output side acts somewhat reverse bias diode. So the collector to base junction at output side is going to act like a reverse bias diode. So the common base amplifier has high output impedance. Here therefore the common base amplifier provides a low input impedance and high output impedance. So transistors with low input impedance, high voltage impedance will provide a high voltage gain. Even though the voltage gain is high, the current gain is very low and the overall power gain of the common base amplifier is low as compared to the other transistor amplifier configurations. Here the voltage gain in this is very high and the current gain is very low. The common base transistor amplifiers are primarily used in the applications where low input impedance is required. Here the common base amplifier is mainly used as a voltage amplifier or current buffer, and this type of transistor arrangement is not very common and is not widely used as the other two transistor configurations. Generally this is not very common. Generally we'll go with collector to emitter configuration and collector to collector configuration. So this type of transistor arrangement is not very common and it is not widely used as the two transistor configurations. So the working principle of PNP transistor with common base configuration is same as the NPN transistor with CB configuration. So only difference is in NPN and free electrons conducts most of the current, whereas in the PNP holes are going to conduct most of the development of current. To fully describe the behavior of a transistor with CB configuration, we need two set of characteristics. They are input characteristics and output characteristics. First, we will go with the input characteristics. The input characteristics describe the relationship between input current and the input voltage. That is emitter current and base to emitter voltage. For horizontal vertical line and first draw a vertical line and horizontal line. The vertical line represents y-axis and the horizontal line represents the x-axis. The input current or emitter current is taken along the y-axis and the input voltage is taken along the x-axis. To determine the input characteristics, the output voltage VCB is kept constant at some value, let us kept at 0 volts, and the input voltage is performed for each voltage level of input voltage of VBE. The input current is recorded on a paper or in any other form. A curve is then drawn between input current and input voltage at constant output voltage VCB at 0 volts. And this is the curve which we are going to get just like the diode characteristics. VCB is equals to 0. And if we can also go with the different values of VCB, we are going to get different the characteristics with different VCB values. Here the output voltage is increased from 0 volts to a certain voltage 8 volts and kept at constant, and then again we are going to take the VBE. When we are varying the VBE, and we are going to note down the VBE and IE values. After keeping the VCB constant 8 volts, VBE is increased from 0 volts to different voltage levels. For each voltage level of input voltage, the input current is recorded on a paper or any other form. A curve is drawn between the input current and input voltage at constant output voltage of VCB is equals to 8 volts. This is the curve which we are going to get at VCB is equals to 8 volts. Here when the output voltage is at 0 volts and the emitter base junction is forward biased by the input voltage, the emitter base junction acts like a normal PN junction diode. So the input characteristics are same as the forward characteristics of normal PN junction diode. Here the cut-in voltage of silicon transistor is 0.7 volts and the germanium transistor is 0.3 volts. In our case, we are taking a silicon transistor. So the above graph which we can see after T is 0.7 volts, a small increase in output voltage will rapidly increase the input voltage. Here when the output voltage is increased from 0 volts to a certain volts, 8 volts, the emitter current is increased, which in turn reduces the depletion region width at emitter base junction. As a result, the cut-in voltage will be reduced. Therefore, the curves shifted towards the left side for higher values of output voltage VCB. Now we will go with the output characteristics. The output characteristics describe the relationship between the output current and the output voltage, that is IC versus VCB. First draw a vertical line and a horizontal line. The vertical line represents y-axis and horizontal line represents x-axis, the output current or collector current is taken along the y-axis and the output voltage is taken along the x-axis. To determine the output characteristics, VBE is kept constant and VCB is increased. So, which is we are going to take the values for VCB and IC. VCB and IC. A curve which is drawn between the output current and the output voltage VCB at constant IE, that is at 0 milliamperes. This is the characteristics where we are going to get a constant value for 15.7 volts. And if we go on increase the input current, that is IE value is at 1 milliampere. So again this value increases, saturation region value increases, and that is equals to IE is equals to 0, IE is equals to 1. Like that we are going to have the output characteristics of bipolar junction transistors under common base configuration. And then here from this we can see that for a constant output current IE, when the output voltage is increased, the output current remains constant. And at saturation, both emitter base junction and collector base junction are forward biased. From the above graph, we can see that a sudden increase in the collector current when the output voltage makes the collector to base junction forward bias. From the above characteristics, we can see that a constant input current and output voltage is increased. The output current is remains constant. The next one is the early effect. Due to the forward bias, the base to emitter junction acts as a forward bias diode, and due to reverse bias, the collector to base junction acts as a reverse bias diode. Therefore, the width of the depletion region at the base to emitter junction is very small, whereas the width of the depletion region at the collector base junction is very large. So here this depletion region problems we are going to get. The base to emitter junction depletion area is very less, and the collector to base junction depletion region is very large. And here the output voltage VCB applied to the collector to base junction, and where JC is further increased. The junction JC will be further increased. Depletion region width is going to further increases. The base region is lightly doped as compared with the collector region. So the depletion region penetrates more into the base region and less into the collector region. As a result, the width of the base region increases. And this dependency of base width on the output voltage is known as early effect. The dependence of base width on the output voltage, which is known as the early effect. If the output voltage applied to the collector to base junction is highly increased, the base to current junction The base width may be reduced to zero and causes a voltage breakdown in the transistor. This phenomenon is known as punch through. The next one is the transistor parameters. In this, dynamic input impedance. Dynamic input impedance is defined as the ratio of change in input voltage to the corresponding change in the output current. Delta VBE is equal delta VBE by delta IE, where VCB value is kept constant. VCB value here it is kept constant. And dynamic output resistance. The dynamic output resistance is defined as the ratio of change in output voltage or the collector voltage to the corresponding change in collector current, that is known as dynamic output resistance delta VC by delta IC. Here the emitter current is constant. The output resistance of common base amplifier is very high. And the next one is the current gain of the transistor in common base configuration, which is defined as the ratio of output current or collector current to the input current or emitter current, where alpha is equals to IC by IE. The current gain of transistor in the CB configuration is less than unity. The typical current gain of a common base amplifier is 0.9 H. In this session, we have discussed the operation of transistor under common base configuration. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.